Hey, let's talk about a new force, which is the elastic force. And it's a different force. The reason it's different, if you think of every other force we've talked about, and we talked about normal force, and we've talked about force of gravity, we've talked about friction, we've talked about tension, force of tension. Okay, whenever you did a free body diagram for those, it didn't change. Okay, so for example, if we're talking about an elevator problem, the normal force and mg didn't change during the course of the problem. Mg doesn't change at all unless we get very far away from the Earth. Force of friction, you could either have static or kinetic. And if I changed an applied force, I guess the force of friction might change, the static force of friction might change, but it wasn't continually changing. You had to one situation and you figured out what the force of friction was or what the tension was and all that. These are constant forces in the problems that we've been doing. Now, springs, which have what's called elastic force, are a little bit different because they definitely can change during the course of a problem. Now, in dynamics problems, we don't really look at them as changing. Okay, we look at it as a constant force at one location. But when we get to energy, there's definitely some change in the force. Let me show you what I mean. Here's a spring. And when we talk about elastic forces, we're talking about springs, stretchy things, rubber bands, anything like that. So a spring has a natural equilibrium position. Okay? That's where it's just at rest, no external forces pushing or pulling on it. If I start to pull it back like this, it will pull in the other direction. So the more I stretch it, the more it pulls back. So if I stretch it this far, and again, let's just draw our equilibrium position all the way down. So this is how long the spring would normally be. If I pull it this far, and we'll call that a delta x, okay? If I pull with this force, then the spring force will be back in that direction. And I'm going to draw these as vectors. Okay, so it's in the opposite direction of the displacement. And this is the force by the spring. If I pull it even further, if I pulled it out here, it would have a very, very big spring force in the opposite direction. Okay? So that's what a spring looks like. That's how it seems to behave. The farther you pull it, the more it pulls back with. And I think you're familiar with this with anything. If you think of resistance bands in physical therapy or exercise, the farther you pull it, the more force it exerts on you. And the more force you have to exert to hold it back that far. But springs, real ideal springs, let me write ideal spring. Ideal springs aren't very common in your experience. Resistance bands aren't ideal springs because they work as a spring when you stretch, but you mash them, they just mash together. They're just like a pile of rubber. Whereas real springs, it takes some pressure to compress them. If you think of shock absorbers and things like that, if you think of the springs in a ballpoint pen, if you compress it, it will push back. So now my delta x is in that direction. That's how far I've compressed it. It pushes back, the force by the spring pushes back in that direction. So there's elongation or stretching, there's compression, but these things are related. And the equation that we have for this, spring force, is equal to, and we very frequently say negative if we're talking about vectors, k delta x. You'll sometimes see it just written as Fs magnitude equals k delta x. In other words, the farther you stretch, the more force required. Here it says the farther you stretch, the more force it pulls back in the opposite direction. I really shouldn't say force required. This is the spring force. That's how hard it pulls back. So the more you stretch, the more it pulls back, but in the opposite direction. And this here is called the spring constant. And you may, with springs, when we talk about labs or problems, you may hear Hooke's law. And this is Hooke's, with an E, law, right here. That the force exerted by a spring is proportional to the displacement of the spring, how much it's stretched from equilibrium, and in the opposite direction. That's basically Hooke's law. For forces, for dynamics, that's it. It's really not that bad, okay, particularly for our AP1 class. It's not bad. All you have to do is keep in mind that for different displacements, it's a different force. So if I have, let's do a little problem here. We could find a spring constant. One way we could find a spring constant is, here's the spring, it's hanging. Okay, it's at equilibrium position. And let's just say it's 0.2 meters long at equilibrium position. If I hang a mass on it and let it come to rest, then I know the free body diagram will look like this. mg, and the spring force, which is equal to kx in magnitude. Okay, and that arrow gives you the direction. And so if I said this is now 0.25 meters, 0.25 meters, and I should put a delta in there, delta x. Okay, then I can do an equation. And let's say that the mass was, let's say the mass is 0.5 kilograms. Well, what do you think? I got a free body diagram. I'll pick a positive direction, and I'll say spring force minus mg equals m times a. And we're letting it come to rest. It's not bouncing up and down. We'll do that when we do simple harmonic motion. We'll do that when we do energy. But right now, in a strict dynamic sense, if I let it settle, so it's at rest, then I know this is in equilibrium. I know there's no acceleration. That means the spring force is equal to mg. And so the way I had it was k times delta x would be 0.05 because it's stretched 0.05 meters. Add mg to both sides equals 0.5 times 10 equals 5 newtons. And this is in meters. I generally don't write the units in the equation. When I divide those, what I will end up having is k equals, and I'm going to write it up a little higher so you can actually see it. K equals 5 newtons divided by 0.05 meters is 100 newtons per meter. Okay, and that's the unit for the spring constant. K equals 100 newtons per meter. And it sort of makes intuitive sense. The spring constant, how hard you have to pull to stretch at a certain distance. So that's really basically the first part of springs. It works for compression, it works for elongation. But notice, if this thing is bouncing up and down, that force is constantly changing because the elongation, that displacement there, is changing the entire time. That becomes a very complicated thing. If a spring is moving through some range of motion, we can't solve problems in our normal way. We have to use energy to do it, which we'll see in a later unit. So, fairly simple for the dynamics unit. Free body diagram using Hooke's law, and solve using Newton's second law.